Welcome back, Leo Lions. This is Mrs. Morgan with today's lesson on exponential functions. So we've talked about 7-6. We've done linear, exponential, quadratic. Today we're going to focus specifically on just exponential functions. So we've learned an exponential function is a function in the form y equals a times b, and then the variable x is the exponent. Now, a couple things about this function or this equation. The value of a cannot equal 0 because anything times 0, it's going to end up being 0. So that won't work out. The b value has to be greater than c. So I'm going to say b is greater than 0, and b cannot equal 1. If b were 1, think about that equation. 1 to any power, 1 times 1, it's always going to be 1. So we need a number different than 1 for that b. So this will give you a function where all the outputs have a common ratio, which is a multiplication factor. So remember, we talked about looking at tables, looking at the pattern and what's happening. In order for it to be exponential, it has to be multiplied by the same number over and over. So remember, a common difference where we are adding or subtracting an arithmetic sequence where you're adding the same values, that is a linear function. And this is how you can tell the difference. So we've kind of done this with our tables. Identify if they're linear or exponential. You could pause the video, see if you're on the right track here. We're looking at our y values to find out what that difference is. So we're multiplying by 3 over and over. So this is a exponential function. And because we are multiplying by 3. To the y values. That's what we're looking at. Okay, as long as your x values are going up by 1, and they are in all of these tables. Now here, this would be, the pattern would be adding 2, adding 2, adding 2. Since we are adding the same thing over and over, this is linear because there is a common difference of +2. And last one, we can see our y values are increasing pretty fast. So times 4, times 4, times 4. So this is an exponential function again, because we have a common ratio. All right, so let's look at some actual story problems and apply these exponential functions to real life. So we can evaluate an exponential function. We're going to substitute a value in for that variable. Remember that the exponent has to be done before we multiply. So we have an initial population. So this is our starting population of 20 rabbits. And they triple every half year. The function, so here we have f of x equals 20 times 3 to the x power. So here we are given the actual equation for it. Remember that f of x is the exact same thing as y. So gives the population after x half-year periods. So it's always important to figure out what is x representing. In this case, they're half-year periods. Here we're saying that it triples every half year. So how many rabbits will there be after 3 years? So if you notice in our equation over here, the 20, that is our starting value of the rabbits. We know that, can't spell initial. We know that it's going to triple every half year. So there's the 3, that's our triple. And then the x stands for half-year periods. Okay, so that's where that equation comes from. Eventually, we're going to be writing those on our own. And I can't spell periods either. So half-year periods. So what we need to do is fill in that x value and solve this, but we got to figure out what we're plugging in for x. So how many rabbits will there be after 3 years? So how many half-year periods are there in 3 years? Well, each year there's 2 half-year periods, so multiply it by 2. This would be 6 half-year periods. So when we plug in that variable x, we're actually plugging in 6, not 3, so be careful. So we will use our equation. So f of x, or the function of x, equals 20 times 3 to the x power. We were given that. In this case, we are simply going to plug in, I'm going to replace x with 6. So when x is 6, we're going to figure out this function. And then that x is now a 6. So like I said, we have to make sure we do exponents first. 3 to the 6th power is 729. And then we multiply by 20. So 20 times 729, we get 14,580 rabbits after 3 years, if they are tripling every half year. Okay? Let's do another one with beetles. So we have 30 flower beetles. So again, this is our starting point. This is our initial. And they're left undisturbed in a warehouse bin. The beetle population, so here it doubles instead of triples each week. So here's our function again. We're given that equation. Now where are these numbers coming from? So the 30, that is our initial. They're doubling, so now it's times 2. And then this is for each week, period. So again, we got to decide what we're plugging in for that x. So give the population after x weeks. How many beetles will there be after 56 days? So this 56 days we need to turn into weeks. So 56 divided by 7 days in a week. So we know this is 8 weeks. So instead of plugging in 56 for that x, we're going to plug in 8. So same thing, I'm going to take the function they gave us. So f of x equals 30 times 2 to the x power. And then in place of x, we're going to put that 8 weeks. So 30 times 2 to the 8th power. Again, exponents first. 2 to the 8th power is 256. So 30 times 200, I wrote it backwards, 256. And that equals 7,680 beetles. And you may use those powers and multiplication. You may use your calculator for those. So 2 to the 8th power, you could plug that into Desmos. Okay? So that's some examples with exponential growth in real life. Now we are going to graph our exponential functions. So we have several things that we're going to identify here. So first of all, let's start out making an XY table. So we're going to pick, I was trying to find my example. So we're going to pick values for x. Make sure that you plug in for x and y. So we want to plug in, we want some negatives, we want 0, we want positives. Oh, and I'm going to go even further beyond just using ones. So we would plug in -1 over here for x. So remember, negative powers are going to end up switching to its reciprocal. So this would be 3 times 1 over 2 to the first power, or 1/2. So 3 times 1/2, we are getting 1.5 or 1.5. Plug in 0. So anything to the 0 power is 1. So that would be 3 times 1. Plug in 1. So 2 to the first power is 2. 3 times 2, we get 6. 3 times 2 to the second power, so 3 times 4, we get 12. So we can kind of see what's happening here. We're multiplying by 2, by 2. So then we'd come over here and we would graph these on our coordinate grid. So negative 1, 1.5, 0, 3, 1, 6. And you're going to notice it's going to increase pretty quickly here, so we won't be able to. Sorry, I'm getting a phone call. So we won't be able to plot that next one at 212 because we'd fall off the graph. It may help to have another negative value though, or maybe another couple negative values. So I'm going to keep going with the negative. So this would be 3 times 1 over 4, 2 squared. So 3 times 1/4 is 3/4, or 0.75, same thing. And then I'm also going to do negative 3. So that would be 1/8. 3 times 1/8. And you're going to kind of pay attention to what happens here. I'm going to keep that one as a fraction, as long as you're able to plot these. So negative 2.75 is about right here. Negative 3/8. You're going to notice this is going to come awfully close to the x-axis, but if we kept going backwards and backwards with these negative values, it's never going to actually touch that 0, that x-axis. So it's going to look something like this. And I'm going to put my x's to show it does carry on in both directions. So this would be an exponential growth. The domain, your x values, are all reals. Your y values, remember, domain, you scan your pencil from left to right. Range, you scan it from up and down. So your range, your y values, have to be greater than 0. All right, they will never go below 0. Your y-intercept, it will never ever touch, oh sorry, I'm thinking of your x-intercept. Your y-intercept is where it crosses the y-axis. So that is positive 3. Okay? We're going to do another one where that first term is negative. So again, you would create your x and y values. Remember to pick some positives, negatives, zeros. So I'm going to start with negative 2, negative 1, 0, 1, 2, and kind of see what happens in this one. So we're going to do negative 0.5 times 3 to the negative second power. So that will flip to negative 0.5 times 1 over 3 squared, and 1 over 3 squared is 1/9. So we're going to end up getting a negative for this one. And we're going to end up getting, let's see, 1/2, so negative 1/18. Ooh, pretty small. Do it again with negative 1, so that will switch to 1/3. So negative 0.5, or negative 1/2 is what I'm thinking of when I'm multiplying, times 1/3, so we'll get negative 1/6. Negative 0.5 times 3 to the 0 power, anything to the 0 power is 1, so negative 1/2 times 1 is negative 1/2. Plug in 1, so negative 0.5 times 3, so we get negative 1.5. 2, so 3 squared is 9, so negative 0.5 times 9, half of 9 is negative 4.5, and you're going to see it's going to drop pretty quickly. So let's graph those ordered pairs, negative 2, negative 1/18. So we're going to be really close, but not on that line. Negative 1, negative 1/6. Drops down a little bit. 0, negative 1/2. 1, negative, ooh, 1, missed that one. 1, negative 1 and 1/2. And then it was 2, negative 1, 2, 3, 4.5. And you'd see we probably fall off the graph on the next one. So again, you can see that curve that's starting to form. And not the best drawn there. And it looks something like this. So this is our example of an exponential decay. Okay, again, domain values, if you scan right to left, exponential functions, we're always going to have all reals here. In this one, our y value has to be less than 0 because it's everything below that x-axis. Our y-intercept then, where it crosses, is that -1/2. So -1/2 is our y-intercept, okay? And last one, how we actually solve equations. Our goal is to get the term with the x by itself. So it's just like solving equations. We need to get rid of that multiply by 3 and divide. So we'd have 2 to the x power equals 8. Once you get there, then we can kind of think about, okay, to what power, 2 to what power gives us 8? So x equals 3. 2 times 2 times 2. Okay, same thing here, except we have multiply and divide. So we want to get this 2 to the x power by itself. Remember, we do the opposite of order of operations, so we'd have to add 152 first. So we get 160, and then divide by that 5. Now we're back to that example above. So we'd have 2 to the x power equals 32. So now you're asking yourself, 2 to what power gives us 32, and that'd be 5. So that's